Okay, let us continue. Last time we discussed one of the simplest but very important examples of quantum many-body integrable systems, which is Calogero Moser model. And today we will look at some generalizations and extensions of this model. The idea is quite similar to what we did last time. Anyway, each generalization of the Calogero Moser model defines some new class of special functions or symmetric polynomials, and some of them are very, very important and have a lot of different applications. This is why we will discuss it today. First of all, let me recall that when we study these models even at classical level, we may write it at classical level, the Calogero Moser model. There is a kinetic energy plus some coupling constant, and here is potential. And in fact, this potential, so what we previously considered is a potential which is 1 over q squared, but this is not a single possibility. Another possibility is to write 1 over sine squared. This is the so-called rational Calogero Moser model. This is the trigonometric case is often called Calogero Sutherland, because Sutherland considered some in the very beginning of the studies of quantum many-body integrable systems, Sutherland studied concretely this potential. And finally, we have also possibility to study the Weierstrass pi function. This is elliptic model, so this is trigonometric. And we have also elliptic model, elliptic Calogero Moser model. Where the potential is a Weierstrass pi function. But we are not going to discuss during our course this elliptic potential, but it can be also solved by some technique. But it is more complicated case. So today we discuss this trigonometric. We begin with discussion of this trigonometric case, and then we also extend Calogero Moser model to the so-called relativistic model of Rosenars type. So, in the trigonometric case, when we study quantum model, we consider the following quantum Hamiltonian. So this is our potential inverse squared sine, which was mentioned here, and the coupling constant is G will be parameterized in the same way as we had it in the rational case. And it is also useful to use exponents of these q's. We denote it like q large, and so we have this set of variables, and we can of course re-express this inverse sign in terms of this q large variables, because the sign of qi minus qj over 2l is equal to 1 over 2I. So what is it here? It is exponent of qi minus qj. This I is, of course, it's just an imaginary unit. And now we may write it like 1 over 2I, square root of qi divided by qj, minus vice versa, qj divided by qi. And finally we have 1 over 2I qi minus qj divided by square root of product. And this means that the sign squared qi minus qj over 2l is equal to minus 1 over 4 qi minus qj squared qi qj. So that we may rewrite this potential very easily in terms of this q large. And of course, using this q large, we may rewrite also this Laplacian. We sometimes will use q small variables, sometimes q large. So it's in fact, the transition is simple. The first statement is so for this model, absolutely the same scheme works, the same recipe as we had it in the rational model. First, we represent this Hamiltonian in the following way by using some kind of annihilation and creation operators, and these are annihilation, creation, and plus energy of ground state. And this ground state energy is equal to nu squared over L squared n squared minus 1 divided by 24. And these annihilation and creation operators are as follows. Annihilation operator, I will write it in terms of small q's, but of course can easily rewrite it in terms of large q's. So the sum is over k not equal to I from 1 to n. And the sum goes over here we have a cotangent of qi minus qj divided by 2l. And this is annihilation and creation is almost the same. The difference is in this sign behind derivative. And the sum is just the same. So this is a statement, and it can be verified straightforwardly. So it's very similar to what we have done. And I think this can be just kind of homework. Now, the second, so this was the first step of our construction. The second step is to define the ground state. The ground state, some kind of which we denoted as delta, and this delta is annihilated by annihilation operator. And this delta is a ground state. It is written as again, it is similar. It is a kind of van der Monde function, but in the power of beta. But now this van der Monde function is written in terms of these q's, q large. And we have also here a product from 1 to n large of qi in the power of minus 1/2 and minus 1 beta, where beta beta is a nu over h. So this is it. And this is a second step, yes, and what next? The next step is to conjugate our initial Hamiltonian with this ground state. So the next step is to make a transformation from h, which was this initial Hamiltonian, to h prime, where h prime is up to constant, is a conjugation of h minus ground state with this ground state. And we also put here coefficient, just for convenience. Let me just explain why it is convenient. It is convenient for the following reason, because it has then the kinetic energy. When in the kinetic energy, if we just substitute here, we'll have this h squared divided by L squared and so on, some coefficient here. But if we put this coefficient in the redefinition of h, then the kinetic energy is just this operator. From 1 to n large. And now the potential energy takes the form. So now we don't have a term with potential energy. So our idea, if you remember last time, was just to conjugate this operator with some function, which is in fact a ground state. And it acts in the following way. It just removes the potential energy term, but adds some term which has some linear dependence on differential operators. And the same story happens here in the trigonometric case. So that we have a sum of q's divided by difference of q's multiplied by qi minus qj d over qj. That's it. And this is just a second-order differential operator, which has a quadratic term, some quadratic terms, and some linear terms. In fact, there are some linear terms sitting here also, yes, because we have here qi, partial derivative of, again, qi and partial derivative. So this, for example, this, when this acts to this q, then we have some linear part of this term also as well. And the solution to this problem is also very similar to what we had previously in the rational case. And now it is called Jack polynomials. They are obtained as follows. We again consider the monomial symmetric functions, symmetric polynomials, symmetric polynomials, which were defined by some partition lambda. This lambda is a partition. And and this in lambda is a sum over all possible permutations of a product of all possible q's in the corresponding powers. So these are exactly the same monomial symmetric functions, but they depend on this q large, which are exponents of the previous q small. And so the Jack polynomial, one can also verify the following statement that so in fact it's not so easy task, but it's just a statement that the eigenvalues for this for these operators are given by the so-called Jack polynomials. Jack polynomials. And these Jack polynomials are constructed as follows. They depend on this set of variables q large. They depend on beta, where beta is a coupling constant divided by h, this nu over h, and as all symmetric functions, it depends on some partition lambda, and it begins with this monomial symmetric function, and then it has some set of terms which are smaller. It's a kind of partial order in partitions, and in this partial order, this mu is smaller than lambda. With some, so we may put it like lambda mu also dependent on beta, and these coefficients are to be found, in fact. So it's just a very generic expression. The final answer includes a concrete set of formulae for all these coefficients. You may find it in the literature. I won't write it here, but this is just a statement that this ansatz, this substitution works, and it provides a correct answer. And it is also possible to define it in some just a second. So I won't write it now, but the set of Jack polynomials can be also defined by some definition, by some universal definition as a set of orthogonal polynomials, orthogonal with respect to some scalar product. But we'll not stop at this place here, but we'll discuss it a little in a little more detail for the next set of symmetric polynomials, which extend these Jack polynomials. So finally, what we have, the statement is as follows. The statement or the theorem is that if we have this new Hamiltonian given by this operator H prime, then there exists a set of Jack polynomials defined by this kind of formula, but I don't put any details, but just a generic expression for it. And they can be defined as symmetric functions, which are eigenfunctions for this operator, with some eigenvalue, and we just we may write this eigenvalue. This eigenvalue is epsilon lambda is a sum over squared lambda i's plus beta sum over I minus j lambda I minus lambda j. So this is an eigenvalue. And the last one step is to move back. So now we have solution at least in terms of symmetric polynomials for this quantum problem, but for this operator. And originally we considered this operator H. So we should move back and make some inverse transformation. And if we do it, so let me write what we have finally. Finally, we have, if we do it, then we have H set of eigenfunctions for this H with some eigenvalues E lambda, and this this psi. This psi is in fact just a product of this G, of this Jack polynomial and the ground state. So what we have here is just a product of Qi from 1 to n in this power of minus n minus 1, beta 1/2. Then we have a Vandermonde function in the power of beta. And finally, it is multiplied by the Jack polynomial. By the Jack polynomial, yes. So this is the answer for eigenfunctions, and eigenvalue also transforms slightly, so it changes after this conjugation. It acquires some additional terms, and these additional terms are as follows. It has nu squared over L squared. So we have this term, and plus h squared over 2L squared, the sum from 1 to n of lambda j plus beta multiplied by n plus 1 n plus 1 minus 2j and lambda j. This is it. This is a correct formula. Yes, it is. So this is the answer. And I just again repeat that this result is very similar to what we had in the rational case. It also useful to mention that in fact this expression which is standing here, this E lambda, can be written in the form of sum of certain quasi-momenta. This pi I quasi-momenta. So it's just another form of the same result, where this pi I equal to h over L lambda n plus 1 minus I plus I minus n plus 1 1/2 multiplied by beta. So just verified straightforwardly that this expression is the sum of these squares. And this is an interesting statement from some point of view. Let me just let me try to explain how it may appear. Maybe not exactly, but at least let me make some comment on it. Before talking about quantum many-body systems, we always discussed different types of Lax representations. At classical level, integrability just formulated in terms of Lax representations, classical R matrices, and so on. At quantum level, when we discussed, for example, quantum spin chains or Gaden models, we again used Lax representations, but they were quantized and they satisfied some quantum exchange relations with quantum R matrices and so on. And we then constructed some monodromy matrices as a product of quantum Lax matrices. So we had the rich construction which was based on the Lax representations. And now what we are discussing here doesn't deal with Lax representation at all. So where is this Lax representation here? And can it be somehow used here, or at least is there any interpretation of these results in terms of this of some kind of Lax representations? So let me make a comment on this topic. First of all, recall that at classical level, in classical mechanics, when we had this Lax equation, then it followed immediately from this equation that the traces of powers of these matrices are conserved quantities. And this was, in fact, based on the following thing. if you compute, if you begin with this equation and compute the time derivative of L in the kth power, then you will easily obtain that it is equal to L in the kth power, a commutator with the same M. And then, this is just because, in fact, when you compute the time derivative of this LK, you use the Leibniz rule. Yes, you use L dot LK minus 1 plus L dot LK minus 2 and so on, all the terms. So you use the Leibniz rule. And the commutator is also a derivation in Lie algebra. So okay, the commutator is also a derivation, and the Leibniz rule works for this commutator just in the same way. So you first use the direct Leibniz rule, then you substitute this commutator instead of L dot, and then you use inverse Leibniz rule because this commutator is again derivation, and then obtain this expression. So then, if you have this, then you just compute trace of both powers and of both sides. I'm sorry, and in the left-hand side you then get this trace of L in the kth power, and here you have 0. But this is based on the simple property that the trace of commutator is equal to 0. Now suppose we are looking for some kind of this Lax equation in quantum case. Maybe it is more convenient to begin with the rational case. For example, in the rational case, I mean, for the rational Calogero Moser model, we had this Lax representation. It was a matrix which had moment on the diagonal, and here some of diagonal terms were of this type. And now consider a quantum Lax matrix, the quantized Lax matrix. So what is the quantization of Lax matrix? Of course, it's just when you put some heads here, heads on momenta and coordinates. And so, for example, let us work in coordinate representation as we did it previously, as we did when we were looking for these eigenfunctions, wave functions. Then we just need to quantize our momenta, and the diagonal term is just the same. And it appears that the Lax equation still works at quantum level in the following sense. This L dot is a Poisson bracket of the Hamiltonian with Lax matrix. And now the quantum Lax equation, says that the commutator of Hamiltonian acting as just some differential operator with this L is equal to L and M. So you see, this H here plays just the same role as M matrix here, but M is some matrix, and this is a scalar operator. So we may write it in components, like L M Ij. Ij is standing here, and Ij is standing here, and it means that it is from k from 1 to n, L ik in kj minus mik lkj. And the M matrix is in fact the same. So we may, M matrix was independent in the classical mechanics. Our M matrix for this model was independent of momenta. It depends on positions of particles only. So that, and in fact it is the same here. So that it di delta ij minus 1 minus the Kronecker symbol. So this is a formula for this M matrix where di this is the M matrix in classical case, and it remains just the same in quantum case. So if you put some head here, then it is just the same, because it is independent of momenta, and it keeps the same form. So you may so this is a statement. In fact, this is a statement which is slightly different from computation in classical case, but not very much. Its right-hand side is absolutely the same, or at least very close to the calculation performed in the classical case. And the left-hand side is just a commutator with this with the quantum Hamiltonian. Okay, now we have this quantum Lax equation, and what to do with it? Here we had some conserved quantities. Can we do some similar trick in quantum case? The answer is no, because so in fact from this equation you may again easily obtain the same relation, the relation which is similar to this one. So that is the commutator of Hamiltonian with kth power of L will be equal to the commutator of this kth power of L, quantum L, with M. But you cannot compute the trace, because if you so of course you may compute the trace, but you cannot use this cyclic permutation on the trace, because these matrices, this matrix L, for example, consist of differential operators. So the elements of this matrix consist of differential operators, and the differential operators are not commutative. So this is why when you compute trace of AB, then you write it like this, and if these are C-valued functions on our phase space, you may write it like Bji A, ij, and then change I to j, writing like B, ij, aj, and finally write it like trace of BA. But if you work in quantum case, this transition is not correct. This is not correct in quantum case. You cannot change A and B, the order of A and B, if they are differential operators, because they do not commute. This is why you cannot use cyclic permutation under trace. And for this reason, there is no such an easy recipe in quantum mechanics for computation of conservation laws. But in some particular cases, and this is indeed a serious problem. I mean, in some more complicated models, in this concrete model, I will just say you an answer right now. Because of some additional symmetry or some additional property. But in the general case, there is no recipe to construct conservation laws. And sometimes for some models, the computation of quantum conservation laws was a very complicated task. For example, for the quantum spin Calogero Moser model, the computation of quantum Hamiltonians provided a very, very nice and very novel ideas for some Jungian symmetry underlying these models. It was in the paper by Godin, Haldane, Pasquier. So maybe we'll discuss it next time. And just this time, I want to explain how to obtain conserved quantities is in concretely this case. In concretely this case, we have additional property. This additional property is that if you compute the sum of elements in M matrix along the row or along the column, then it is equal to 0. How it happens? You see, for example, let me write this M matrix. The first row, this D1 minus nu Q1 minus Q2 squared minus nu Q1 minus Q3 squared. This is a matrix in 3 by 3 case, and this D1 is exactly equal to Q1 minus Q2 squared plus nu divided by Q1 minus Q3 squared. So as you can easily see, the sum of all elements along the row is equal to 0. And the same happens along any column. And then, if we have this property, then you can just make some correction in the classical recipe. So let us look at this equation. H L to the power of k is equal to the commutator of L to the power of k with m. So this equation holds true still. Yes, because we just have commutators in both in left-hand side and right-hand side. And so when we compute, again, when we compute it by using of the Leibniz rule, it works in the same way in the left-hand side and right-hand side. So now, and this is like ij. And now let us compute not the trace, but the total sum. Total sum. Total sum. It is denoted as TS, and it is equal to the sum of all elements, not only diagonal elements. In the trace of some matrix, you compute the sum of diagonal elements, and in the total sum, you compute the sum of all elements. Then here, in the right-hand side, you have the sum of I L to the power of k, I, say this is L small, M L J minus M I L this is L to the power of k, I L, and M L J M I L multiplied by L to the power of k, L J. And if we compute the total sum, then we sum up here over J, and we also sum up here over I. And this gives us 0. After summation over I and J, this provides 0 and this provides 0. And for this reason, we obtain a set of operators which commute with initial Hamiltonian. But it happens by only this very special property of this model, that this sum of elements along the row or along the column equals to 0. It also works, in fact, in trigonometric model. So for this model, which we just discussed, the same statement holds true. Because if you put here, so in the trigonometric model, you just need to put here sign. The sign of Qi minus Qj divided by 2L. And the same thing happens here. Here and here. So this works just absolutely in the same way, and you may compute the conserved quantities. But for example, in the elliptic case, I also mentioned today the elliptic case, the one with the Weierstrass pi function. In the elliptic case, there will be no such property, and the computation of quantum elliptic Calogero Moser Hamiltonians is a more complicated task. It doesn't work in this way. The next thing, so this is a comment on Lux, on quantum Lux representation. But the next thing is that we can use also a characteristic polynomial. One possibility for computation of conservation laws in classical mechanics is to compute the traces of powers of L. And another is just to write the characteristic polynomial. For example, you may write it like 1 minus determinant of 1 multiplied by lambda minus L is equal to 0. This is a characteristic equation, but so you may also look at this expression standing in the left-hand side. And just if you look at this expression here, so maybe we just don't need even characteristic equation, but we just need this determinant, which is a generating function of also some Hamiltonians, because they are just the coefficients of characteristic polynomials that can be expressed through the traces of powers. Obviously. And so what I want to say? I want to say let me put plus here. I want to say that there is a there is an analog of this characteristic polynomial in quantum case. So in quantum case, we may put here a kind of determinant lambda plus L hat. But in order to compute this expression, you should also explain how to compute the determinant of a matrix which elements are operators. So you need to define some rules. So you need to define an order of elements. And we, for example, defined it as normal ordered expression when all momenta are moved to the left and all coordinates are moved to the right. And my statement is as follows. Yes, and just let me also mention that this determinant is equal, in fact, to the product of lambda plus lambda I, where lambda I are eigenvalues of this Lax matrix. So these are just action variables, classical action variables. Classical action variables. And now let us look at this quantum operator and quantum expression. Let us fix that we choose a normal ordering here, and let us write it again in some form like lambda to the power of I, and here we put some quantum Hamiltonians. Now let me formulate a statement. Statement or theorem. Consider the following expression. We choose this ground state, which we used here previously, so this ground state, yes? And we conjugate this differential operator with this ground state. And let us call it d hat of lambda. Then this d hat can be computed explicitly and it has the form, let me write it explicitly. The product, so we have a Vandermonde, the coefficient of a Vandermonde, then we have a sum over permutations. This is a sign of permutation. And here we have also a product of over I from 1 to n, qi to the power of n minus this sign of permutation.
What is this? The normal order of the determinant equals to the sum of number times hi theta. What's this hi theta?
Sorry?
What's this hi theta?
I didn't write explicit expressions for this hi.
So this is definition of h.
This is, yes, this is kind of definition of h, of these operators.
How this normal order works? It's like we first compute the determinant as like we attend, we don't.
Yes, you may think about it as follows. You compute it as classical one by thinking about this derivative as some pi I. Then move all pi I to the left, and or to the right, maybe, I don't remember, maybe to the right. And then replace them with these differential operators.
So first we compute it like everything is commute, and then
Yes. Then move all momenta to the right, and then replace them by quantum analogous. So let me just finish this expression because it's a curious fact. And so this, after conjugation of this determinant with this ground state, we obtain some expression. Which we call this d hat, and this d hat of lambda, maybe it's not good to use this lambda because I had notation for lambda was a Young diagram. So let me write it here, d of w. This w stands means the same as lambda here. D of w applied to Jack polynomial depending on lambda, where lambda is a diagram partition. Yes, it provides this some eigen. So these Jack polynomials are eigenfunctions for this generating function of quantum Hamiltonians. And this lambda large of w is equal to the product from 1 to n of w minus pi j, if I'm not mistaken, maybe a plus. I'm not sure about this sign, but maybe it is correct. Where this pi is exactly this quasi-momenta. So this is very similar to what we had in classical case. You see, in classical case, this characteristic polynomial for the Lax matrix is an expression depending on this eigenvalues of classical Lax matrix. So these are just classical action variables. And in quantum case, we just considered a quantization of this polynomial with a normal ordering, then conjugated it with the ground state, then obtain this differential operator depending on some parameter lambda, which maybe it is better just to denote it right here by w. And so I can see where it is here. Yes, this is w. Yes, this is w. And now the Jack polynomials are eigenfunctions for these operators with and eigenvalues are exactly quantum analogous of this expression, where the role of action variables play this quasi-momenta, which we obtained here in this eigenvalue in this eigenvalue. Okay, this is the story. This is the story how to involve the Lux representation into this construction. And now let me also talk about the next model. And the next model is the so-called Rusinard-Schneider model. So let me write the definition, and I will also just formulate main results concerning this model.
I'm sorry, I have a question. For example, in the classical case, you read the determinant of lambda plus L, but lambda is a multi-index plus L is a matrix.
So what do you mean by multi? Oh, no. This is not. This is what I just tried to tell you, that because it's so I should put some W here. I changed here lambda to W because lambda is a standard notation for the variable of characteristic polynomial in classical case, and in quantum case lambda is a partition. This is why. So I hope.
It's not a partition.
So here it is not partition. It's just it should be some variable W, and but here and we should put also W here. Then this is a generating function of operators in this variable W, and the partition appears here in the eigenfunctions. Okay, let us talk about Rusinard-Schneider model, and we just from the very beginning let us talk about trigonometric. About trigonometric model. This is a generalization of Calogero Moser model, first of all. And main idea, in fact, is that the Calogero Hamiltonians are polynomials in momenta. So, and after quantization, these polynomials in momenta become some differential operators. It's because we substitute some straightforward quantization of momenta as differential operator. And in the Rusinard-Schneider model, we have difference operators. So let me give you some generic definition, and then I explain what does it mean. So we have the set of difference operators, and this S plus minus K is equal to in fact it is maybe not very easy definition, but we have what we have. So this sum goes from for all subsets of this set of indices of length k. So for example, when length of this subset is equal to 1, it's just sum over all possible indices. Or when k is equal to 2, then it is a sum over all pairs of indices, and so on. And here we have a product of I belong to this J, and J not belong to this J large of also plus minus this the two possible variants for plus k and minus k. We have this two set of functions, qi minus qj. Then here we have a product of some operators, which are difference operators, and I will explain how they act. And finally, again, the product of the same functions but now the arguments are qj minus qi instead of qi minus qj.
Sorry, I have a question. In the expression of the h hat, you have L over 2, right?
No, there's 1 over 2, just 1 over 2, 1/2. These h plus minus functions are as follows. H plus minus functions, qi minus qj, are in fact ratios of signs 1 over 2L, qi minus qj plus minus I nu, but this I is an imaginary I, plus minus I multiplied by nu, divided by not shifted sign, so the same sign without shifts, and all this square root. And this is a definition of function of this function h, and we also have this this operator t, and this operator is just a tk plus minus is just a shift operator. Yes, shift operator. So it shifts a function by this coefficient. Yes, when you have a differential operator in the so you have an exponent of differential operator, then it's just a shift operator. It acts on the function of this q's variables, and the action of this operator is a shift of the corresponding variable by this coefficient. Or we may put it differently. If we have, for example, we previously used the notation for where we had this qj, which were exponents, and then this t plus minus k, the action on some function, on arbitrary function, is just a multiplication of the corresponding argument qk by q small in the power of plus or minus 1. So the shift operator acts on q smalls by shift, and the action on exponents of coordinates, if you shift these small q's, then you obtain just a multiplication of this q large by some q small, where q small is this coefficient multiplied by Planck constant. Q, and the rest of q's is unchanged. So this is a definition. It's quite complicated, even the definition is not very easy.
I'm sure one thing in the definition of h, and you have some L. Is L the same as the index L in G? Because you take sum of L.
This L here,
Yes,
yes, this L is just exactly the same L.
and it's the same as L in.
Oh no, no, this no, it's just an. This is just an index. Maybe let us put it like some, I don't know, S. Too lot of letters are needed. So this is a definition of this quantum difference operators. And what Rosenares showed in his one of his original papers is that the set of difference operators commute. In fact, he wrote conditions for commutativity of these operators, and these conditions appear to be some functional equations for this functions h. And these functional equations for this function h can be resolved, and one of the possible variants is when h is this function. And it has, in fact, it has rational analog, just like, in fact, its rational analog is obvious. You just should remove sign from here and from here, and you will get the ratio of this expression divided by this expression, and then this is a rational Rosenares-Schneider model. And if you put here a theta function, the Riemann theta function instead of sign, then you will get the elliptic model. And it also works, and his functional equations are valid for this, for elliptic model as well. And this model is a generalization of the Calogero Moser model. I think we have no time today to discuss solution of this problem, but let us at least discuss why it is a generalization of Calogero Moser model. Let us write S1. S1. So k is equal to 1. We write this, the first, this difference operator. You see, now when k is equal to 1, the sum goes over all one-dimensional subspaces in this set of indices, so it's just a sum over all possible index. So it's overall over some index j, a sum over some index j. The product here is over I, which is not equal to j. So the product is over I, and I is not equal to j. And here we have h plus of qi minus qj. And we should put here tj, and here we should put also h plus qj minus qi. Yes, this is it. No, we should also put, maybe not like this. So in fact, we should put it again here. I over I not equal to j, h plus of qj minus qi. That's it. So this is our expression for S1, and let us compute it. Let us look at it in an even more simple case, in classical case. In classical case, this Tj is just an exponent of momenta. Yes, because we just substitute, in fact, this momenta, maybe momenta with some coefficients, I don't know, divided by, let us have a look, divided by L or something like that. So some coefficient. I will write moment divided by C. And then in the classical case, we have S1 without head. Without head. We have a sum from 1 to n of, now we just unify h plus qi minus qj and h plus qj minus qi. We unify the products of two functions, and we put also this exponent of momenta. So this is expression for the Hamiltonian, for the classical Hamiltonian, where this product is in fact can be computed, and it is not some complicated task. We just multiply this expression by the same expression where the sign is changed, and if you do it, you will see that this expression is in fact the square root of 1 minus sine squared I mu divided by sine squared qi minus qj. And so how it happens that this expression...
There's some L you forget.
Sorry?
Maybe there's some L here.
Should be L somewhere here, yes. Yes, the L should be everywhere, in fact. It should be here, and it should be here, yes. And so after, yes, so in which sense this system generalizes Calogero Moser model? We may consider the following limit when this let us put epsilon here. So we redefine this constant c in such a way that epsilon goes here, and we redefine this nu in the way that we have also epsilon here. Let us just put additional epsilons here, and then consider the limit when epsilon goes to 0. Then this exponent, so the meaning is that we have these difference operators, and these difference operators, if you expand the exponent, turns into differential operators. And in the classical mechanics, the exponent of momenta turns into some polynomial functions of momenta. So if you compute this limit, then you find that this S1 begins with some n, then in the first order in epsilon it has sum of momenta. How it happens? Because here we have 1, and this is of order epsilon squared because of this sign here. And even if you compute the square root of this, then nothing will change. I mean, this again will of order square epsilon squared. And so this sum of momenta appears as, because this is 1 plus epsilon pj over c plus and so on. And then and you also have the sum over all indices. So this is why in the first order you will obtain this sum. And in the second order, you see, in the second order you will obtain something which has momenta squared, and the expression coming from this square root which has inverse of signs. And we have a product of these expressions here, the products of all i's, and this products over all i's will provide us 1 plus epsilon squared plus a sum over I, a sum of all I not equal to j. And we have also a sum over j here. Yes, so I mean that after some not complicated calculations, you will find out that you will exactly obtain the Calogero Hamiltonian here. So it should be done accurately, but I hope you may see that it works. So in the first order you obtain the sum of momenta, and in the second order in epsilon you'll just need to expand the product of all these square roots. All they give you just some kind of a sum over I of these inverse signs, and you have also a sum over j. So this is why you will have a sum over two indices for the inverse sign squared. And the sum of squared momenta comes from this exponent as well. So this is a generalization, in fact, of Calogero Moser system. And why we are discussing this model is because these operators, Rusinard-Schneider operators, by some conjugation with ground state, turns into the so-called McDonald operators. And these McDonald operators have a lot of applications. And the symmetric functions corresponding to McDonald operators are McDonald symmetric functions and McDonald polynomials. And they are widely used in many different areas of mathematics and physics. This is why this model is important, and so we'll finish next time. And here we stop for today.